Over here. Nah. Here. Yes. Hi James. Hey, the question I sent you, actually it is a second derivative. Really? Because I find that surprising because when I found the first derivative was equal to the answer you said was the answer. What's that? The first derivative is equal to what you said the answer was supposed to be. Is it? Mm-hmm. Okay, maybe I'll make a mistake. Because I remember I saw it too, it was d2y, dx2, but it is possible that I'm absolutely mistaken. Sure. Okay, that would make sense because finding the second derivative, the arithmetic is really, really gross. I did do it, but the problem was the arithmetic didn't match the final answer. Sure. And I probably like 10 times. I'll get the same answer, but it wasn't with me. But that should be the answer. Please do fill out the attendance form when you have a chat. Second, scan one of those QR codes. Okay, you're right. First derivative. Yeah. Okay. We can still go over it. Sure. Okay. Yeah, it's worthwhile. Yeah, shouldn't be that hard as first derivative, but still, it is a problem. Sure. So. Also, you can figure out that one problem you showed us earlier, right? With a circle. I don't remember what problem you're referring to. I can find it later. You told us that it would take you a while and you're going to try it later. It was circle and you were trying to prove that the distance between each point to a specific point is a certain amount. Do you remember that at all? No. I can find it after class. You mentioned the problem here and then it was like you won't have time to go over it. Was it the problem where I don't think it was a circle? Maybe it wasn't. It was something like between some points on one point had to be a certain amount. I think the problem you're thinking of is the one where you had like the square root of x plus the square root of y equals the square root of c. Yes, that's it. Yeah, I did figure that. Yeah. Okay. I'll consult time. Sure. I tried it. I couldn't figure it out. It's a little challenging, but it's not too terrible. Okay, so let's look at. So I was planning on mostly talking about. Well, that's not very descriptive. Mostly about like finding extrema, relative maxes, relative mins, inflection points, that kind of stuff. First derivative, second. But before we get to that, let's talk a little bit about a couple things just to make sure everyone. So I just want to remind everybody of the inverse trig derivatives, specifically because there's one problem I want to look at. I think throw away some pens here. I know we've talked about them before. This pen's okay. Time to buy some new pen. I know I keep saying that. I actually do it. So you probably want to commit these to memory because they come up just often enough that you probably need to know them. Interesting. So I'll remind everybody of the three that you need to know. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. The derivative of the inverse tangent of x is 1 over 1 plus x squared, or x squared plus 1, either way you want to write it. So we'll write it one way, it doesn't really matter, right? This or this.
Same deal. Brighten this up just a tiny bit here. And then finally, the one that's a little controversial, the derivative of the inverse secant of x, depending on how your classes define secant, you may or may not have an absolute value. I'm usually thinking of it like this: 1 over x, absolute value of x times the square root of x squared minus 1. But it could be, depending on your class, it could be that they have said the derivative of the inverse secant of x is 1 over x times the square root of x squared minus 1. And you just have to kind of be careful. You have to do what your professor said, right? So whichever way your professors defined it, take note of that, do what they said, such as life. And then the other three, if you know these three, you know the other three automatically. The derivative of the inverse cosine of x is just the negative of the derivative of the inverse sine of x. It's negative 1 over the square root of 1 minus x squared. And the derivative of the inverse cotangent of x is the negative of that one, which is negative 1 over x squared plus 1, or 1 over 1 plus x squared, either way you want to write it. And finally, the derivative of the inverse cosecant of x is negative 1 over the absolute value of x, square root of x squared minus 1. So nice to know. You know these three, you know these three. And then, of course, if your teacher has done it the other way, or the derivative of the inverse cosecant of x is negative 1 over just x, square root of x squared minus 1. There is something worth pointing out here, because it's going to come back up in 21B when you talk about trig substitution. So I would really encourage you to actually make these connections, because there's a really nice thing to see, and that's the following. If you were to plug in the corresponding trigonometric function to any of these places, meaning if I were to plug in, so let me write this down here. So in 1 minus x squared, if I plug in like x equal to sine of theta into 1 minus x squared, you get a trig identity. And it's not like a coincidence, it's on purpose. It happens that way because of how we set this thing up in the first place. Check this out. 1 minus sine squared theta is equal to cosine squared theta. And it works for the other ones as well. If you plug in x equal to tangent theta into 1 plus x squared, you get 1 plus tangent squared theta equal to, we all know this one, I tan and get secant. 1 plus tangent squared theta equals secant squared theta. And then finally, for the third one, if you plug in x equals secant theta into x squared minus 1, you get secant squared theta minus 1, which you can see from this one above is just equal to tangent squared theta. You don't need to focus too much on this right now, but it will tell you later on when you talk about trig substitution in 21B, the way we typically identify how to make the trig substitution is by looking for a 1 minus x squared or a 1 plus x squared or an x squared minus 1. And if you see a 1 minus x squared, you're going to pick sine because of this. And if you see an 1 plus x squared, you're going to pick tangent because of this. But the thing is, if you remember what your inverse trig derivatives are, you'd be like, oh yeah, I remember the derivative of inverse sine is 1 over 1 minus x squared. So if I see a 1 minus x squared, I should use sine. Similarly, that for that, that for that. So that's kind of what I am hoping you remember later on. And I'll definitely, like, if you're in Co-21B next quarter, I'll be like, hey, remember that thing we talked about? This is now we're going to use it when we talk about trig substitution. So that's definitely a good plug for actually memorizing the inverse trig derivatives. I know they're kind of a pain, but they're not that bad. But the real reason, well, not the real reason, one of the reasons I want to talk about this is because there was a question that someone had that's a little bit challenging and has an inverse trig in it. And where'd you go? So it's an implicit differentiation problem, which is good to practice every once in a while. So let's say we're given the following. Let's keep the notes in order, James. It's always a challenge. So we're given, yeah, this is gross. It's not that gross. We're given the arc cosine or the inverse cosine of xy times y is equal to negative 3 pi square root of 2 over 4 at the point, and we're asked to find, so we want to find y prime at the point 1/2 comma negative root 2. And being the person I am, when I saw the problem, I checked to make sure that it was a point that was actually on the graph. Not that you normally should do that, because even if it ends up not being a point, your teacher still probably wants you to do the process anyway. But if you plug that in, we can see that the arc cosine of, let's see, 1/2 times -√2 times -√2 is really the arc cosine of -√2 over 2 times -√2. So we're looking for the angle. We're looking for an angle whose cosine is equal to -√2 over 2. So what angle do we take cosine of that gets us -√2 over 2? Well, it's not pi over 4, because cosine of pi over 4 would be +√2 over 2. It's 3 pi over 4, because we have to be in quadrant 2 for the inverse cosine. And that works, right? That means this is going to equal 3 pi over 4 times -√2, which is exactly what that is there. So check. Well, so this is actually, so let's go back to the inverse trig function for a second, because that's a really good question. So we'll come back to this. So specifically, the inverse trig functions are defined, have very specific ranges. So the problem with inverse trig functions is we kind of all have to agree on what the range of an inverse trig function, I'm going to emphasize the word function here, is because when you have a function, you can only get one output for every input. So if I have, f of x equal to the inverse sine of x, for example, and I want to say find, f of pi over 3, which is the inverse sine of pi over 3. Oh, I blew it. That's not the, I mean, I didn't blow it, but you couldn't actually find that. So I'm making a bigger error here in that I'm plugging in the wrong sort of thing, or I should be plugging in the value and getting out the angle. But the less big error I've made here is you can't even take the inverse sine of pi over 3, because pi over 3 is bigger than 1. And this does not exist, because you can't take the inverse sine. You can't find an angle, the big sine of that angle, you get something bigger than 1. If you're trying to find inverse sine of x equal to theta, that's the same as saying sine of theta is equal to x. But sine is always between -1 and 1, so we can't get inverse sine equal pi over 3. Also, it's a weird number to think of, right? You normally would say what I really meant to say here was, let's find f of 1/2, because then I want to find the inverse sine of 1/2. I'm looking for the angle. If I take sine of that angle, I get 1/2. Now, you might say, James, there's a lot of answers to that question. And there are many, 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 literally infinitely many angles that if you take sine of that angle, you get 1/2. But there's only one angle that we've all agreed is the answer. Or we've agreed is the output of this function.
Can we go over all the inverse derivatives?
Yeah.
Inverse trig derivatives and mark which quadrants they're.
Sure. Well, I would say the inverse functions, because the derivatives, the ranges are a little bit different. But yes, sorry, getting text. So yes, just give me a moment here. So inverse sine of 1/2 is the angle whose sine is equal to 1/2 is pi over 6. Yes, I know the sine of 5 pi over 6 is 1/2. I know the sine of 13 pi over 6 is 1/2. There's many, many angles, but we have agreed that the range of the inverse sine function is specifically -pi over 2 to pi over 2. Which is different than the range for inverse cosine, which is also frustrating, but true. So for example, if I wanted to find f of -1/2 equal to the inverse sine of -1/2, the answer is in quadrant 4, but it might not be the angle in quadrant 4 that you would usually think of. The answer is not 11 pi over 6. The answer is -pi over 6. Because sine of -pi over 6 is equal to -1/2, and -pi over 6 is between negative pi over 2, and positive pi over 2. So, yeah, it's worth going over this again. Yeah. So let's briefly kind of hash the inverse trig functions because they are worthwhile and I know they can be confusing. So let's talk about where they all come from. Yeah, sorry. But yeah, let's finish this other problem first, though, just because we kind of started it, and it's not too much worse to get through. So we'll come back to the inverse trig functions in a moment. If there's anything specifically any of you want to see about inverse trig functions, let me know. But back to this problem here. We had this equation, arc cosine of xy times y equals negative 3 pi root 2 over 4. And we're trying to find y prime, or someone might phrase this as find, instead of writing y prime, they might say, find the slope of the tangent line. At the point 1/2 comma negative root 2. Same question, just phrased a different way. So I'm going to first and foremost take the derivative of both sides, differentiate. Okay, so the arc cosine of x has a derivative that is negative 1 over the square root of 1 minus x squared. The derivative of the arc cosine of some stuff is going to be negative 1 over the square root of 1 minus our stuff squared times the derivative of that stuff, which I'm just going to leave as is for a moment, times y. So I have to use the product rule here. I've got the derivative of this piece times that piece left alone, plus, do it the other way, leave the first piece alone, multiply by the derivative of the second piece, which is just y prime, equal to the derivative of all this is 0, because it's just a constant. I have to do a little bit more work, because I have to take the derivative of xy. So I'm going to get, let's see, let me pull this y over here. So I'm going to write this as negative y over the square root of 1 minus xy squared times the derivative of xy is going to be product rule, 1 times y plus x times y prime, plus still arc cosine of xy times y prime. And here's what I recommend almost always when I'm dealing with finding the slope of a tangent line or the derivative at a particular point using implicit. After you've differentiated both sides, that is the moment of opportunity. That is when you want to plug in your point typically. I don't want to do all the algebra solving for y prime right now. I could, it's not that terrible, but it's usually going to be somewhat easier just to plug in your point right now. So I'm going to plug in x equal to 1/2 and y equal to negative root 2. Which kind of ran out of room, so let's go down here. So plugging in x equal to 1/2, y equal to negative root 2, I'm going to get, let's see, negative is positive root 2 over square root of 1 minus x times y is negative root 2 over 2. Negative root 2 over 2 squared times y, which is negative root 2. Plus x, which is 1/2 times y prime, which we're trying to find, plus the arc cosine of negative root 2 over 2 times y prime equal to 0. And now it's just dealing with all this arithmetic, which isn't too terrible, but we do have to be careful. So let's be a little bit careful here. So I've got, let's see, root 2 over negative root 2 over 2 squared is 1/2. 1 minus 1/2 is 1/2. And the square root of 1/2 is the square root of 1 over the square root of 2, or 1 over root 2. I know that's a lot, but it's not that much. Let's double check. Yeah, 1/2, 1 minus, yep. So I could have just written 2 here if I wanted to, right? Root 2 times root 2 times negative root 2 plus 1/2 y prime. We already said the arc cosine of negative root 2 over 2 is 3 pi over 4. Again, we'll get back to that, but the reason being that the arc cosine function has a range defined to be from 0 to pi, quadrants 1 and 2, times y prime equals 0. So let's see, simplifying this, that's just a 2. So distributing this 2 to each of those terms, I'm going to get negative 2 root 2 plus y prime plus 3 pi over 4 y prime equal to 0, or y prime times 1 plus 3 pi over 4 equal to positive 2 root 2, or y prime equal to 1 plus 3 pi over 4. Sorry, that's not quite, James. Y prime equal to 2 root 2 divided by 1 plus 3 pi over 4. If I multiply the top and bottom by 4, I get 8 root 2 over 4 plus 3 pi, which was the desired answer. Kind of gross. Oh, sorry, you can't see that. Yeah.
If you express the 1 half, that's the 1 half. If you express that as square root of 2 over 2,
Mhm.
it's also possible. You get the same answer, but
Yeah.
it looks so different.
Sure.
I think that's the mistake I made in the first derivative, because I'm plugging that into the second derivative, it made it terrible.
Sure, but again, you shouldn't be looking at the second derivative here because they're not really asking for the second derivative. Question.
Pop the numerator and denominator by 4 to get rid of that fraction.
Yeah, that's what I did. Yeah. So I multiplied by 4 over 4 to get to that. Typically, we like to express our answers so there aren't fractions in fractions. So if we have fractions, we usually do a common denominator kind of thing to get rid of them. Okay. Other questions about this? About this interesting problem. Papers everywhere. Let's get a little more organized over here. Okay. You don't want to skip around. Done with you. Done with you. Done with you. Cool. Okay. All right. Let's stay with them. So let's go back. A lot of my favorite pens. Okay, it's fine. Let's go back and talk about inverse trig functions for a bit, because I know we talked about them a while ago, but some of you are coming up on them now and they can be a bit confusing. So let's do it. So typically when I'm thinking about inverse trig functions, I'm thinking about taking my trig function and limiting its domain so that I can invert it. So here are the functions we're going to look at. We start with y equal to sine of x. In fact, this is true for all trig functions. None of the trig functions are 1-to-1. What does it mean to be 1-to-1? Yeah, passes the horizontal line test. That's a great way. That's usually how I would say it. Or you could also think of it as its inverse is not going to pass the, if it's not 1-to-1, its inverse won't pass the vertical line test. So that's why we need a function to be 1-to-1, is so that its inverse actually is a function. So here's y equals sine of x. Again, I'm just kind of giving you the basics. Let's go negative pi over 2, pi over 2, pi, and so on. Okay, I'm just going to start using other colored pens, I guess. Blue is my favorite. Like this. And it continues on. As you can see, it's not 1-to-1. So what we do is we restrict the domain. Yeah. Okay, fine. All the pens have done. So we just limit ourselves to negative pi over 2 to pi over 2. Now, you might ask, and you would be right to ask, why did we choose this section? There are lots of other equally good sections that are also 1-to-1. You get to pick pi over 2 to 3 pi over 2, or 3 pi over 2 to 5 pi over 2, or negative 3 pi over 2, right? There's a lot of good choices. Why do we choose this? I don't know. I can make some good arguments. We typically choose the first quadrant from 0 to pi over 2 because it's easy, right? All the angles in that quadrant, or all the values in that quadrant have nice positive, or sorry, all the angles have nice positive values when you take sine or cosine or tangent on them. And then if you pick this section here, it makes sense to pick the section adjacent to it where it's still 1-to-1, because then you have a nice relatively continuous function. So you can make a decent argument for that's why you pick the domain, why we limit the domain for sine to be from negative pi over 2 to pi over 2. So that when we draw the inverse function, sorry, I'm still trying to hold on to this blue pen here. Right, we interchange the domain of the range. So here's our inverse function. Starting down here at -1 comma negative pi over 2 and going up to +1 comma positive pi over 2. And it looks like you've taken that section of the sine function and just kind of flipped it over. line y equals x, and you have. And here the domain is everything from -1 to 1. And the range is everything from -π/2 to π/2. Okay, I'll give up on this point. Fine, you're all dead to me, dead to me. Yeah, there's some other pens here. What'd you get? See how many pens we can kill a day. So, for example, if you're trying to find the inverse sine of -√3/2, we're looking for an angle. The angle that if you took sine of that angle, you would get -√3/2. And I never know what that is, to be honest. I'm always thinking of the positive version. I'm thinking, what's inverse sine of +√3/2? Or what's the angle that if I took sine of that angle, I get +√3/2? And the angle would be π/3. And so if I'm looking for inverse sine of -√3/2, I know the angle is going to be -π/3. Which is super convenient for inverse sine. Inverse sine, all of the negative values just give you the corresponding negative angle. Nice. So if I'm looking for, gosh, sorry, I know I had like one good pen in here somewhere. If I want to find the inverse sine of -√2/2, same deal. Somewhere there's a pen that can write. I know the inverse sine of +√2/2 is just π/4. This is going to be -π/4. It's not so easy for inverse cosine, unfortunately. But this is kind of the idea, is that we can find our inverse trig function as a function this way. So whenever you're trying to evaluate inverse sine of something, you either get a positive angle in quadrant 1 or the corresponding negative angle in quadrant 4. But you're definitely not going to get 5π/3. You're definitely not going to get 7π/4. I know those angles, we kind of think of them as the same. The right word to use actually is they're coterminal. They end at the same place on the unit circle, but they don't actually have the same value. -π/4 is like, if I pretend that pi is about 3 for a second, -π/4 is like -0.75-ish. Very, very ish there. Whereas 7π/4 is like 5-ish, more than 5. So very different numerical values here. And this is the only right one to use. This is the only right one to use. Questions about this so far?
Will you show columns where instead of a place on the unit circle, it'll be x, like sine, the arc cosine of a fraction of x in it?
Sure, we could look at something like that. It's actually, so meaning I'm guessing you mean something like find the arc sine or the inverse sine of 9 minus x. It's like that. So, well, let me ask you, are we being given anything else other than this? Or like, what are they asking us to do with this? Oh, okay, sure. That's a whole, yeah, we can definitely talk about that in a minute for sure. But the idea basically is to use your usual derivative rules and then apply the chain rule version of that. Well, we'll get to that in a minute.
That was the equation.
Mhm.
Some angle.
Mhm.
So we just take the sine on both sides, but if you do that, do we have to restrict our sine answer to the range of our sine?
Yeah.
Okay.
Yeah.
Okay. Yeah, that makes sense.
So, yeah. I feel like there's more to say here. So let's continue on. Yeah, let's get deep into it for a second here. So here's what I'll say about the inverse sine function even more specifically. If I want to find, say, like the sine of the inverse sine of x, it seems like it should always be x. And it is mostly. Here's what I mean. Let's say we wanted to find, for example, the sine of the inverse sine of, I don't know, 1/2. This one might work out. I might be thinking of it backwards. It's fine. So inverse sine of 1/2 is what? I don't know, pi over something, pi over 6. And sine of pi over 6 is 1/2. Great, check, works out, seems reasonable. So when does it not work? I think it works all the time. That's not true. It works all the time as long as the thing you're putting in there is inside the domain of the function. So you couldn't take the sine of the inverse sine and say like 3. Because the inverse sine of 3 doesn't exist. There is no angle you take sine of that gets you 3. So this doesn't exist because 3 is not in the domain of the inverse sine function.
But the opposite way is true.
The opposite way, well, so let's talk about the opposite way, because the opposite way is interesting. So this is equal to x as long as x is in the domain of the inverse sine function, which is negative 1 to 1. Oops, sorry, you can't see that. Whereas the inverse sine of x is a little more interesting. Let's take a look. It's going to be x some of the time. So let's see what I mean. Let's find the inverse sine. I know this is going to feel silly. The inverse sine of the sine of pi over 3. Okay. So sine of pi over 3, well, let's see. We know that sine of 1/2 is pi over 6, so sine of pi over 3 is root 3 over 2. So the inverse sine of, oops, no, that's right, yeah, of root 3 over 2. Is that sine of pi over 3? What's the angle whose sine is equal to root 3 over 2? Pi over 3. Okay, so you might think not very interesting. I would agree, not very interesting. But now let's look at the inverse sine of 2 pi over 3. What's sine of 2 pi over 3 over in quadrant 2 with the same reference angle? Well, it's sine of pi over 3. Right. And now, what's the inverse sine of root 3 over 2 equal to? And it's right there. It's pi over 3. So they're inverse functions for values that are in the range of the inverse sine function. And for other values, you have to kind of go back to that original range. So I would say the inverse sine of x is equal to x for values of x that are in between negative pi over 2 and pi over 2. But for values outside of that domain, we get different things. We get essentially the angle that has the same reference angle, and you have to decide whether you're in quadrant 1 or quadrant 4.
I wonder where this one earlier in the class, but I just want to make sure I remember it correctly. The domain of the composition is the range of the inside function that lies in the domain of the outside function.
That sounds about right.
So it's a for that's general term, right? For any composition, the domain of the composition is the range of the inside function that falls to the domain of the outside.
Sure. So then you have to find the domain of the inside function that
Which
is
is
the
the
range.
intersection of the range of the inside and the domain of the outside.
Probably.
Okay.
So, but here is what I would say is the domain of this function is everything, right? You can take sine of any value. Just your outputs are going to be very limited. So for example, if I wanted to find the inverse sine of okay, here of 7 pi over 4. Well, 7 pi over 4 is in quadrant 4. Sine is negative there. It's a pi over 4, so we know it's a root 2 over 2. So this is going to be the inverse sine of negative root 2 over 2. And the inverse sine of negative root 2 over 2 is negative pi over 4. And the same would be true if it was the inverse sine of the sine of 5 pi over 4. Sine of 5 pi over 4 is also negative root 2 over 2. And the inverse sine of negative root 2 over 2 is still negative pi over 4. So typically, when I see something like this, I'm thinking about my reference angle. So here's the thought process I am going through when I'm trying to do this without doing too much work. If I want to find the inverse sine of say, I don't know, 7 pi over 6, I would say, okay, great. My reference angle definitely pi over 6, for sure. So then I know my answer is either going to be positive pi over 6 or negative pi over 6. I just have to determine if it's going to be positive or negative based on, is sine of 7 pi over 6 positive or negative? Well, sine of 7 pi over 6 is in quadrant 3. Sine is negative there. So this sine of 7 pi over 6 is negative whatever, and the inverse sine of that is going to be negative pi over 6. Now, normally I'm not trying to shortcut my work that way. So really, I would actually probably do the work and say, oh yeah, this is the inverse sine of sine of 7 pi over 6 is negative 1/2. And then the inverse sine of negative 1/2 is indeed negative pi over 6. So that's kind of some of the thought process I'm going through here. People ask other weird questions about this too. But I feel like someone could ask you, like, just to carry on with this for a minute here, what's the tangent of the inverse sine of negative 3/5? I know what the inverse sine of negative 3/5 is. Neither do you. Nobody, I mean, that's not true. Someone probably knows it like by heart. It's something, I don't know what it is actually. It's an angle. It's probably 50-ish degrees, 58. I don't remember what that is exactly. Something. But that's not the point of the problem. The point of the problem is we can draw a triangle. And when you're dealing with inverse trig functions, that is often what they want you to do, is to draw a triangle. Meaning, sure, I've got other pens. Inverse sine of whatever, you should always be thinking of as an angle. That is an angle. And I can draw a triangle to go with that angle. And if sine of my angle is equal to 3/5, okay, I'm ignoring the negative sign. 100% I'm ignoring the negative sign. Just bear with me for a second. So sine of my angle is equal to negative 3/5, but I'm going to ignore the negative. So opposite over hypotenuse. Sine of my angle is negative 3/5. Sure, fine. And then my other side, I can use the Pythagorean theorem to find. In this case, it's our usual lovely 3, 4, 5 triangle. 3, 4, 5 right triangle. So then the question is, well, what's tangent of this angle equal to? Well, tangent of this angle is opposite over adjacent. But is it positive or negative? Yeah, what quadrant does my angle live in? Well, if I'm taking inverse sine of a negative number, it's in quadrant 4. And tangent is negative in quadrant 4. So this is going to be a negative answer. On the other hand, if I said, what's cosine of inverse sine of negative 3/5? Well, I still use the same triangle, but now my angle is in quadrant 4, and cosine is positive in quadrant 4. So cosine of this angle is going to be positive 4/5. Kind of neat. Kind of annoying. Kind of neat. So in the same way we've talked about inverse sine, we can briefly talk about inverse cosine. And inverse cosine looks very, very similar, just a little bit different. In fact, we can just draw it right here. So I'd love more pens that worked. So I'm going to draw a cosine, and then we go specifically from, I'm going to draw the part I need. Let's start at negative pi over 2 and go all the way to 3 pi over 2. So cosine does this, 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 and this. Like that. There's your code. Oh, sorry. It's so out of frame. And just like before, we see that cosine, like sine, like every trig function is not 1-to-1. Every trig function is not 1-to-1. So we're going to limit its domain. And we have to make a different choice here. Because if we pick from negative pi over 2 to pi over 2, not 1-to-1 still. We're going to pick from 0 to pi. Our domain is from 0 to pi. And the inverse function, y equal to the inverse cosine of x, is going to have a range from 0 to pi. And instead of having 0, 1, we're going to get 1, 0. Instead of having pi negative 1, we're going to have negative 1 pi. It's going to look like this. There's your inverse cosine function. I would point out, just to point out, since we're here, if you think about the derivative of this function, that derivative is definitely going to be undefined at the endpoints. Because those endpoints, you have a vertical tangent line, and vertical lines have undefined slopes. Which also makes sense if you think about what the derivative of inverse cosine is, right? It's 1 or negative 1 over the square root of 1 minus x squared. If you plug in 1 or negative 1, you get division by 0. So definitely undefined at those endpoints. Which is kind of interesting. So then we can say things like the inverse cosine of 1/2 is pi over 3. And the inverse cosine of negative 1/2 isn't negative pi over 3, it's 2 pi over 3. Because we're looking for the right angle that's in either quadrant 1 or quadrant 2. It's got to be in quadrant 2. I should say right angle. I should say the correct angle in quadrant 1 or quadrant 2. And then you can do all sorts of similar-ish things. I don't really want to, but we can. You could say something like, sorry. For example, brain. Oh my gosh. Yeah, the inverse cosine of something like root 3 over 2. Sorry, I keep getting, oh man, my brain is just sometimes keep going the wrong way there. Sorry about that. The inverse cosine of pi over 6 is going to be something like the inverse cosine of root 3 over 2, which is pi over 6. But then if you pick an angle that's not between 0 and pi, like inverse cosine of 7 pi over 6, the cosine of 7 pi over 6 is negative root 3 over 2. And the inverse cosine of negative root 3 over 2 is 5 pi over 6 in quadrant 2. Okay. So I feel like we've talked about kind of the weirdness of the inverse cosine function enough, in that you've got this weird range issue, right? Where when you plug in a value, we all have to kind of have agreed on what our outputs are going to be. And one sec. So I will just point out that for f of x equal to the inverse cosine of x, the range is 0 to pi. And to go along with that, I will also say the following. If your function is the inverse tangent of x, the range is negative pi over 2 to pi over 2. So for example, if we're taking the inverse tangent of 1, we're going to get pi over 4, whereas the inverse tangent of negative 1 is negative pi over 4. It works a lot, very, very similarly to inverse sine, which is nice. And to be perfectly frank, we don't really talk about it for the rest of the inverse trig functions. You can, it's not like it's undoable, but people really don't. So for example, we could talk about inverse cotangents. So if I look at f of x equal to cotangent of, oh, sorry, you had a question, man. Okay. So look at f of x equal to cotangent of x. Cotangent's never my favorite. Cotangent's cosine over sine. As vertical asymptotes when sine is equal to 0, which is at 0, pi, 2 pi, 3 pi, any multiple of pi. So I've got vertical asymptotes there, there, there. And it looks like this. It goes down from left to right instead of up from left to right. It literally looks like you've taken tangent and shifted it pi over 2 and then flipped it over, which really you have. And so if I was going to pick an interval where cotangent would be 1 to 1, I would probably pick from 0 to pi. which I'm questioning myself right now because I don't actually know if that's the same choice the book makes. I feel like it must be. It seems like the right choice. Okay. So f of x equal to the inverse cotangent of x. Instead of having vertical asymptotes at 0 and pi, it's got horizontal asymptotes at 0 and pi. And then it's going to look like, well, flip it over. I always have to think, really, here's what I'm thinking about when I do this. I'm like, okay, I'm just switching x and y. So instead of x getting close to pi and y going down to negative infinity, we're going to have y getting close to pi and x going down to negative infinity. So as I go towards negative infinity for x, y is going to get closer and closer to pi. We do this kind of thing. And then over here like that. Pi over 2. And then you can answer questions about limits. You can be like, oh yeah, the limit as x goes to negative infinity of the inverse cotangent of x is equal to pi. How exciting. It is kind of nice to see what this function looks like, because then you can really convince yourself that the derivative of this is always negative. Right? Any tangent line slope, definitely negative. And we've talked about, we'll see it again, because I feel like I should show you again. But the derivative of the inverse cotangent is negative 1 over 1 plus x squared, which no matter what you pick for x is always going to be a negative value. Kind of cool. This one here?
Yeah, because I understand what you're doing. You're getting an angle and you're putting sign which is you define as opposite of the hypotenuse, or you're finding this pair side. But I'm having a hard time reconciling this conception with the unit circle conception, because the way that I thought about inverse sine of -3/5 is the y-axis length that is -3/5.
Sure.
But if that length is -3/5, wouldn't the other triangle have to follow that?
Sure.
So would that make the same triangle? Oh, yeah.
Yeah. So you can always take whatever your triangle is and divide by the hypotenuse length to make it fit in the unit circle. We just don't usually because it's easier not to.
So it's just the ratio.
Yep. Which is all trig functions are. Trig functions are just ratios. Cool. All right. And then the sad news is about inverse secant and inverse cosecant. We talked about this before, but inverse secant and inverse cosecant, there isn't agreement on how they're defined. So really, if someone asks you, let's talk about, we'll talk about inverse secant, sure. So here's where life gets challenging, meaning you have to just do what the professor says. So y equals, I never graph secant, like it's just not something I do without first graphing cosine. So here's cosine. I'm going to draw it dashed because I don't really want it. Pi over 2, pi, 3 pi over 2, 2 pi, negative pi over 2, negative pi, sure. Let's see. So cosine is 1, and then 0, and then negative 1, and then 0, and then 1, and then 0, and then negative 1. Sure, looks like this. Cool. And then if I'm graphing secant, which is just 1 over cosine, I'm using the zeros of cosine to know where my vertical asymptotes are going to be, because if cosine is 0, 1 over cosine is going to be undefined in a vertical asymptote sort of way. We get vertical asymptotes at pi over 2 and 3 pi over 2 and any odd multiple of pi over 2. And then the actual secant graph itself is going to do the reciprocal thing from cosine. So if cosine is getting smaller, secant is going to get bigger. It's going to do this. And the same thing over here. And here it's going to do this. Cosine gets closer and closer to 0. Secant gets further and further away from 0. And so on, forever and ever and ever. Now, the problem here is that there isn't agreement on which two pieces we should use for restricting the domain. Some people restrict the domain 2, and I'm gonna write it in the actual official way, from 0 to pi over 2 union pi over 2 to pi. We can't actually include pi over 2 because it's not in the domain of the function. Or some people restrict the domain to still the same. You always get the first quadrant. You're always getting 0 to pi over 2 every time, no matter what your inverse function is. But the other portion we're going to use is instead of from pi over 2 to pi, we're going to go from pi to 3 pi over 2. Which would make it tough to actually evaluate the inverse secant function. Right? If someone said, what's the inverse secant of 2? I'd be like, okay, well, let's see, cosine. So I'd really be thinking of the inverse cosine of 1/2. Right? I'm trying to find the angle whose secant is equal to 2, meaning the angle whose cosine is equal to 1/2. I know that cosine of, do I know the cosine of? Yeah. Cosine of pi over 3 equals 1/2. So I'm pretty sure the inverse secant of 2 is equal to pi over 3. Because secant of pi over 3 is equal to 2. But I only know that because I really know that. But here's the bummer. If someone said, hey, find inverse secant of -2, I would have to ask you, well, how have you defined inverse secant? Because it depends on how you have told me you have defined it. If you've defined it this way, great, then my answer is going to be an angle in the second quadrant. My answer is going to be 2 pi over 3. But if you defined it this way, my answer is going to be an angle in the third quadrant, which is going to be 4 pi over 3, which is a bummer. So this is wholly dependent on how, based on how we've defined it. Such is life. And the same is true for inverse cosecant. So your teacher, and I imagine there's variety between your teachers. Some of your teachers might have defined it this way, some of them might have defined it this way.
2 possible domains for inverse cosecant.
Good question. I was hoping you wouldn't ask. No, it's a good question to ask. So actually, first, since we're going to get into it, let's go ahead and draw both the inverse secants as well, and then we'll deal with inverse cosecant, just to be super clear about it. So, let's see. So for y equals inverse secant, or f of x equals inverse secant of x, one way of drawing it's like this. So I'm just using this graph over here, right? I'm looking at this section and this section. So I'm going to have, instead of the point 0, 1, I'm going to have the point 1, 0. And instead of having a vertical asymptote of pi over 2, I'm going to have a horizontal asymptote of pi over 2. And so having the point pi comma -1, I'm going to have -1 comma pi. And the thing I like to remember about doing it this way is that both of my sections are getting closer and closer to this vertical asymptote, meaning both of my sections are getting closer and closer to this horizontal asymptote. So we're going to go like that. And like that. And what I would point out is, just as an observation, whatever the derivative is here, the derivative is for sure going to be always positive. Because all my slopes of my tangent lines are positive.
If this is the definition that we're using in class, then there wouldn't be absolute.
There would be absolute value.
There would.
Yes. Think about the derivative you want. The derivative, if you want it to always be positive, you need the absolute value in there so that when x is negative, you still get positive outputs.
Oh, I see.
That's what then that, and this is where the kind of issue comes into play, because we would like to make this choice, in my opinion, graphically. This is the better, nicer, more obvious graphical choice. It's also got the same domain restriction as cosine, which seems like the better choice to me, but it's got the worst derivative because it's got an absolute value. Or you can make the choice well, you can't make the choice. Your teacher has made the choice for you that the inverse secant of x is this thing, where you still have the same right side, but now your left side still starts at the point -1 comma pi, but instead of getting closer and closer to the horizontal asymptote pi over 2, it's going to get closer and closer to the horizontal asymptote 3 pi over 2. So it's going to do this, which is funkier.
So then this one doesn't need the absolute.
This one does need the absolute value. Yeah. Let me show you. Let me just show you. So what we can talk about finding the derivatives again if you want to. But let me just tell you what the derivatives are. If we do it this way, the derivative is the one with the absolute value. Where is it? And we'll say more in a minute. If you do it this way, you do not need the absolute value. Let's talk about why. If you pick, let's say you pick x equal to -2, which, okay, if x was -2, I'm about right there. X is -2, I'm about right there. My derivative should be positive in this version. If I plug in -2, I get 1 over 2, right? Because the opposite of -2 is 2 times the square root of 3, which is positive. So here, f prime of -2 is 1 over the absolute value of -2 times the square root of -2 squared minus 1, which is 1 over 2 root 3. Positive, as the graph indicates it should be. Over here at -2, my slope should for sure be negative. And when I plug in -2, I definitely get 1 over -2 root 3, as it should be. So that's why we need the absolute value for this one and not for this one.
Well, why is it that we have to add the absolute value? Because doesn't the graph just graph what the derivative is? Doesn't the algebra already make it so it's always positive?
It's because of what quadrants we were in. The fact that what we end up getting when we do the derivative, there's like a secant and a tangent in there. Right.
Shouldn't that make it positive itself?
Well, the thing is, well, so let's first, we'll come back around to that. So let's answer the other question, which was, what does inverse cosecant look like? So I think that's a fair question, because honestly, a question I never think about, because I'm always trying to avoid it because it's kind of terrible. So let's look at cosecants. And when I graph cosecant, I think about graphing sine first. Maybe we'll get to some graphing stuff today. So cosecant, I'm graphing sine. So sine starts at 0, and then pi over 2 goes up to 1, and then the pi goes back to 0, and then 3 pi over 2 goes down to -1, and then 2 pi, you're back to 0. And then negative pi over 2, negative pi. So sine looks like this. Kind of. And then when I'm graphing cosecant, I'm just thinking of using my zeros as vertical asymptotes. We have vertical asymptotes at x equals pi, x equals 2 pi, x equals 0, x equals negative pi. And then I say this a lot, and I think of it this way. I think of cosecant as being the sine graph, but flipped away from the x-axis. So instead of kind of going down like that, it's going up like this. And they do touch each other at that peak there, because sine of pi over 2 is 1, and 1 over 1 is still 1. So cosecant of pi over 2 is also 1. And similarly here, we've got that section there. And then over here, that section there. Okay. So I actually don't know what we choose, to be honest. I haven't thought about it in a while. So it looks like one choice of the domain that we're going to restrict it to could be negative pi over 2 to 0, union 0 to pi over 2. If we make that choice, I'm just picking this section and that section. Both have the vertical asymptote of x equals 0. So if I graph the inverse, we're going to have the horizontal asymptote both being closer and closer to 0. So instead of the point pi over 2 comma 1, I get 1 comma pi over 2. And we go like this. And instead of getting the point negative pi over 2 comma negative 1, I get negative 1 negative pi over 2. Still the vertical asymptote meaning horizontal asymptote getting closer and closer to 0. So that's what the inverse cosecant of x looks like one way. And this way is the way that requires the absolute value. Because here the derivative is always negative. So my derivative here is equal to the negative 1 over the absolute value of x times the square root of x squared minus 1. Okay. So now we have to ask ourselves, which is the other section we should pick? I'm always picking this first section. I can't pick this section because it wouldn't be 1-to-1. So the question, and I honestly don't remember the answer. I might need to look in a book. Do we pick this section here is what I think we pick, or do we pick this section over here, which is what I don't think we picked? I'm pretty sure we picked this section. Sure. It's possibly in the textbook. It might not be. I need to use the restroom. Okay, you look it up. I'm gonna use the restroom, and I'll be right back. It also might not be. There might not even be agreement on that. It could be a thing where some people do it while most people like possibility. All right, do you have consensus? It's okay if we don't. Sure, right, that's what I would do as well.
Yeah.
But the problem with that is that derivative has an absolute value, which is not a problem per se, just it is something sometimes other people try to avoid. So the other choice I'm just gonna make a choice because it'll be fine. I'm gonna say the other option would be to say the domain is going to be, I still want 0 to pi over 2. Union, I don't want that section. I guess I want this section here from pi to 3 pi over 2. Exciting times. So then here's what the graph would look like. I still have this, oh, that's not my best coordinate access system ever. So it's still gonna have this same section over here, because I'm still getting this same first section here. So I'm gonna have the point 1 comma pi over 2. It's gonna go down, down, down like this to the right. But then, instead of having this section down here, which corresponds to this section over here, I'm gonna have this section over here, which is starting at the point 3 pi over 2 comma -1. So I want -1 comma 3 pi over 2. I need to go, am I gonna be able to go high enough? Yeah, we should be fine. And then we're gonna get closer and closer to the horizontal asymptote y equal to pi. Probably the worst of all the graphs, like visually, like it just looks so asymmetric and not nice, but someone could define it this way. If they defined it this way, and then they ask you a question like, what's the limit as x goes to -infinity of the inverse cosecant of x? Your answer might be 0 if you define it that way, or it might be pi if you define it this way. Terrible. And then finally, well, not finally, the derivative of this would be -1 over the x times the square root of x minus 1. Again, notably, right, this function, the derivative is always negative. So no matter if you're plugging in a negative value for x or a positive value for x, you need this thing to turn out negative. Whereas this function's derivative is positive on the left, negative on the right. So if you plug in a negative x value, you need to get a positive result, which you do. Right, look at this. If you plug in a negative x, you get negative, negative, positive. So the whole thing's positive. Plug in a positive x, you get negative, positive, positive, which is a negative. So it works out. Okay. So let's talk about the derivatives. Actually, let's have one more thing before we talk about the derivatives. One more thing we can do, just because it's kind of, well, there's a point. I promise you, there is a point. What if I said, I want you to tell me what the cosine of, all right, let me make sure I do this the right way. Sorry, I have to think about this for just a second. That should be right. Yeah, cosine of the inverse sine of x. Which is a question that comes up on occasion. In homework problems, I've definitely seen it in books. Well, here's the idea. Inverse sine of x, we can draw a triangle. If I say that the inverse sine of x is equal to an angle, aka sine of that angle equals x, aka sine of that angle equals x over 1, I can draw a triangle. So let's see, sine of my angle is the opposite over the hypotenuse. And I can find the third side by using the Pythagorean theorem. Question mark squared plus x squared equals 1 squared. So question mark squared equals 1 minus x squared. So my question mark is the square root of 1 minus x squared. And then if I want to find cosine, well, cosine of the inverse sine of x is just cosine of theta, which is the square root of 1 minus x squared over 1. So you could find the cosine of the inverse sine of x by doing this, which is actually useful, which we'll see in a minute. So finally, working back around to the derivatives. Should we talk about how to find the derivative of the inverse cosine or inverse differential? Should we just say what they are? I'm happy to show how to find them again. If anyone wants to see that. Going once, going twice. Let me show one of them. Cannot show. I know we did it before, but show it again. Sure. Let's do one of sine or cosine first, and then we'll do one of cosecant or secant. So if I want to find the derivative of, sure, inverse sine of x. There are many is probably an overstatement. There's a few ways of doing this, but I'm gonna show you the normal way, which we've already done before. So we're gonna let y equal the inverse sine of x. We rewrite this as sine of y equal to x. And then we differentiate both sides implicitly. So if we differentiate, what's the sine of y? Right, cosine of y times y prime or dy dx. And the derivative of x is just 1. So check this out. Our derivative ends up being 1 over cosine of y. Which, if you were going to write a not very satisfying but technically correct answer, you could say was 1 over cosine of the inverse sine of x. But no one wants you to write that answer. What we want to write instead is 1 over the square root of 1 minus x squared. Because the inverse cosine of cosine of inverse sine of x is exactly square root of 1 minus x squared. Which we don't usually do this way. Usually you would get to this point and you would draw the triangle again. You'd be like, oh, sine of y equals x, which is x over 1, and then you would draw the same sort of triangle that we just drew there. And say, oh, my angle is y, sine is x over 1, the missing side is the square root of 1 minus x squared, and then cosine of that y is the square root of 1 minus x squared. It's exactly this right there. Yeah.
So where is the relationship between the actual sine tangent and secant and the full functions? Cosine. So the reason that the derivative is always the opposite in sine is because as one increases, the other decreases because they are complementary angles.
Sure. I mean,
to go one angle higher, the other angle has to get lower because the overall has to be 180, right?
sure.
Is that
I mean, that's true in the first quadrant. You could say something similar, but you're right. You could say as long as if the sine value is increasing in absolute value, the cosine value is decreasing.
that's what they are?
What do you mean by opposite?
In terms of their derivatives, they always have negative sign of the other.
Sure, the derivative cosine is negative sine, the derivative sine is positive cosine.
Is that the reason, the thing that we just went over? Whereas the absolute value of one gets larger, the absolute value of the other gets less.
I don't know if that's a true statement. It could be, but I'm not really sure. So that's how you find the derivative of triplet. And so now to answer that question you had a while back. Sorry, what's your name? Sorry, what was that? Wow. I would like to say that correctly. Can you say that again? A Stein. All right, Stein. To answer your question from before, Stein, now we can find the derivative of something like inverse sine of x minus 9. I think yours is actually inverse cosine, but whatever. So if I want to find the derivative of the inverse sine of some stuff, yes, of course I can. I'm just using, well, I know that the derivative inverse sine of x is 1 over the square root of 1 minus x squared. So the derivative inverse sine of something more complicated is 1 over the square root of 1 minus whatever that stuff is squared times the derivative of that stuff, which in this case is just 1, which is not very exciting, but it's something we can ask. We can make it more complicated though. I can say, what's the derivative of the inverse sine of x squared plus 5? And then it's still 1 over the square root of 1 minus my stuff squared. And then the chain rule dictates that I must multiply by what? Exactly. Which in this case is 2x. Or I could say, what's the derivative of the arc sine of x cubed times e to the 5x? It's gonna be way more complicated, but still the same idea in that it's still just, right, inverse sine, arc sine, people use the notation interchangeably, get used to seeing both. It's just gonna be 1 over the square root of 1 minus your stuff squared times the derivative of your stuff. In this case, the derivative of our stuff is going to require the product rule. So the derivative of my stuff is going to be 3x squared times e to the 5x plus x cubed times the derivative of e to the 5x. Well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. I probably said the word stuff like 1 billion times in my lifetime because it's the word I always use. Stuff is it's the stuff. And you're always, when you say stuff, that is the verbal reminder that, oh, that there's stuff in there. I better be multiplying by the derivative of that stuff. So as soon as I hear the word stuff or say it in my head, I'm like, oh, there's a derivative of stuff I have to multiply by. So you can find the derivative of all the inverse trig functions in the same sort of way. For example, well, I will tell you because I don't want to do it again, but just like we found the derivative of inverse sine to be 1 over the square root of 1 minus x squared, it is true that the derivative of the inverse cosine is the negative of 1 over the square root of 1 minus x squared. And I would encourage all of you to look back at the previous page and to do that work on your own at some point. Start off with this, except inverse cosine, and then say cosine of y equals x, and then take the derivative. Okay, fine, we can do it. Like, no, you do it on your own. And then you take the derivative of both sides, you get negative sine of y times the derivative equal to 1, and then you get the derivative equal to 1 over negative sine, and then you draw the triangle for cosine of y equal to x, and you can find that it's going to be exactly the same thing, so it's negative. And that's true for all the inverse co-functions. Inverse cosine, inverse cotangent, inverse cosecant. They're just the same, but negative of the regular inverse trig functions. Regular is such a terrible word, though. It's of the not co-functions. I wish there was a better name for them. Maybe there is. I should look it up. So let's look at tangent real quick, just to have all of them on the books again. So if I want to find the derivative of the inverse tangent of x, it's going to be, well, I'm going to start off with y equal to inverse tangent. I've got tangent of y equal to x. I differentiate both sides. I get secant squared of y times y prime equal to 1. I solve for y prime. And I don't really like to, but some people like to write this as cosine squared of y. But then once you get to this place where you've isolated y prime, but it's in terms of the not variable you want, then you need to draw a triangle. This same triangle idea is going to come back in 21B when we talk about trig substitution. So don't ignore it. It's a good thing to do. It's way easier than any other way of doing it. So I should point out, you could do this a different way. You could totally find that 1 over secant squared of y is going to be 1 over 1 plus x squared by using a trig identity, which is really the same thing as drawing the triangle. The trig identity you could use is, hey, tangent squared of y plus 1 plus tangent squared is equal to, you guys are like, yeah, cut it out. Equal to secant squared of y. So you could just say, oh, secant squared of y is 1 plus tangent squared, which is really 1 plus x squared. Because we've said tangent of y is equal to x. So you could totally say, oh, secant squared of y is just going to be 1 plus x squared. Totally works. But that's not that people usually do it, because people just don't like to do it that way. I don't know why. It's easier to do a triangle thing, because for tangent of y equal to x, okay, that means tangent of y equals x over 1 equals opposite over adjacent. And that third side, Pythagorean theorem, is just going to be the square root of 1 plus x squared. So if I want to find cosine of y is 1 over that. So cosine squared is 1 over that squared, which is exactly 1 over 1 plus x squared. It's really the same thing. It's just a different way of viewing it. Question?
Going back to
Yeah.
is that a big thing in like how you get what it's talked about?
Well, we'll talk about that in a minute. So and the answer, unfortunately, is it depends. The answer is yes, I will be the teacher for Co-21B next quarter, which is going to be on Monday, Wednesday, Friday. I forget what time I told you it was all at. 1 to 2? Okay, yeah. Right. That's true. Because you can't. It's not so much on purpose. I mean, I guess it's on purpose. If someone made a choice. It's not, so it's not a class you can register for to get units next quarter. It is.
Is that,
What's that?
why is that?
Because technically next quarter is the quarter I'm supposed to not have to teach any classes, but I said I really want to teach this class and my 16C class following up because like, I mean, you guys could have a different teacher, that would be fine. Someone else might be better, but I wanted to do it because I like teaching you all. So we left it as a class you couldn't register for in case I decided to not teach it and to do more just like office hours. So that's why. So yeah. So no, you can't sign up for it with the unit, but you can. Actually, let's take a look. We'll take a look in a little bit. But yes, I'll address that question more later. Yeah. Yeah, it'll still be a totally canvas that you can set. Basically, we'll do the same thing many of you did this quarter, which is you'll sign up on some Google form and then you'll get added to the campus.
Same place, right?
Good question. Okay, let me just answer the questions now. Let me look at my Google Doc real quick here. Oh, that's big. Why is it so big? Okay, 1 second while I figure out. Let's see. Let me get the sheets. Am I not logged in? I'm not okay. All right, 1 moment, please. Let's see here. Also, here's the attendance form for all of you on Zoom, just in case you didn't already get it. Let's see here. We're talking winter 2023 schedule. Let's see. Yeah, so Co-21B will be Monday, Wednesday, Friday from 1 to 2 in this room. Yeah, in here. 1 to 2, Monday, Wednesday, Friday. Everyone got that? Let me put them right out here. So Co-21B, Monday, Wednesday, Friday, 1 to 2, 110 to 2 in 3216 Duncan Hall. 3216, the room you're currently in.
Yeah, I just forgot.
Yeah. You're welcome. Please, so save that spot in your schedule. I don't think. Well, let's look at the AATC website real quick. Sure. I don't think you can sign up to actually do it yet, but let's see. Winter. Where are you at, winter? Where are you at, winter? There you are. So let's throw it up on the board so everyone can see. I don't know if you can actually see it yet, but if you go to the tutoring.ucdavis.edu/math website and click on here for our co-classes and such, scroll down. 21B, no CRN, complete the registration form that should be available on December 1st. If it's not, check back December 2nd. The person who manages the website has a lot of responsibility, so it might not be ready when they say it will be, but it'll be ready close to them. But yeah, so save that spot in your schedule. Again, if that doesn't work for you, right, if the time is bad for you because you have another class you have to take at that time, that's okay. You can still register or be added to Canvas, especially since attendance really won't matter next quarter because there's no passing or not passing the class, but you can still be added to Canvas. I'm still going to record it just like I have been this quarter, so you can still watch the videos later. Yeah, so definitely sign up when you can, if you want to, even if the time doesn't work for you. Cool. All right, back to the math at hand. Whoops, not that. There was something I was going to say. Oh yeah. So then we can, so just like with the inverse sine, inverse cosine stuff, you can say what's the derivative of the inverse tangent of x squared over sine of x. If I was going to do this one, I might try to make my life a tiny bit easier. If you're dividing by sine of x, I really kind of like to avoid the quotient if I can. I might rewrite this as the derivative of the inverse tangent of x squared times cosecant of x. Just make it a little bit easier. Because I typically think of the product rule as being easier than the quotient rule, but that's just me. And then I know the derivative of the inverse tangent of x is 1/1 plus x squared. So the derivative of the inverse tangent of some stuff is 1/1 plus the stuff squared times the derivative of the stuff, which is going to require the product rule. It's going to be 2x times cosecant left alone plus x squared times the derivative of cosecant, which is negative cosecant x cotangent x. Sorry, I didn't leave myself enough room there. Apologies.
Is there a parallel for trigonometric inverse derivatives and normal inverse derivatives? Because we had a theorem when one over the derivative of the inverse, the corresponding point. It doesn't apply here.
It doesn't apply here. You can totally find these derivatives by using the inverse derivative theorem. I do not recommend it.
Okay.
It's just not as clear. Like doing it this way, at least to me, makes the most sense. I would also say that's true for functions in general, though. Like I wouldn't ever normally use the inverse derivative theorem to find any derivatives of inverse functions. I would always just do some rewriting and find the derivative. Or maybe use the implicit differentiation if we need to. Like, for example, if you're finding the derivative of the natural log of x, you wouldn't really do it using the inverse derivative theorem. You would do it by starting with, y equals natural log of x, rewriting it as x equals e to the y, differentiating both sides, and then solving. Because I rewrote one, so I have x squared divided by sine, which is the same as x squared times 1/sine. And 1/sine of x is the same as cosecant of x. You don't have to make that change, though. You could totally have written the derivative as 1/1 plus your stuff squared, which is x squared over sine of x squared, times the derivative of that stuff, which then we're going to use the quotient rule for. So that's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. That would be a perfectly legitimate way of doing it as well. It just feels messier to me. But they're both correct. They're both the same. They're just written differently. Okay. So now finally, to go back to the ones that are less than excellent, inverse secant and inverse cosecant. Well, I should also point out. So likewise, just like the derivative of the inverse tangent of x is positive 1/1 plus x squared, the derivative of the inverse cotangent of x is negative 1/1 plus x squared. And you can see that if we look back at the graphs for just a second. Or you could also, again, I think it's a good work to do the work for that. But if you look back at the graph of the inverse cotangent, oh yeah, its derivative is always negative. Oh yeah, that thing is always negative, no matter what you pick for x. Excuse me. Now we come to the fun part. So let's look at the derivative of the inverse secant. So we start with y equal to the inverse secant of x. We'll hold off on making any comments about domain and range until we need to. So we're going to rewrite this as secant of y equal to x, and then we're going to differentiate. And the derivative of secant of some stuff is secant of the stuff times tangent of the stuff times the derivative of the stuff. Right? Secant's one of those weird ones where you get the argument showing up twice in your derivative. There's not a lot of functions like that. In fact, the only other one I can really think of is, well, cosecant, but also like inverse secant and inverse cosecant. Right? Those are kind of the only functions where you take the derivative of something and that something shows up in two different spots. I think. I can't think of another like basic function where that happens. So if I take the derivative of both sides, I get secant of my stuff times tangent of my stuff times the derivative of my stuff equal to the derivative of x, which is 1. And then solving for y prime, I get y prime equal to 1 over secant of y times tangent of y. I know that secant of y is equal to x. And I'm not thinking about any of the opposite value stuff at all right this moment. I'm just trying to figure out what this looks like in terms of x, because I don't want to write my answer just in terms of y. If we start off with a function of x, our derivative should also be a function of x. So then I'm going to use a triangle. Say, I honestly don't remember what secant is. Secant of y equals x over 1. I know secant is the reciprocal of cosine, and cosine is adjacent over hypotenuse, so secant should be hypotenuse over adjacent. So if my angle is y, the hypotenuse should be x, the adjacent should be 1. And the third side, I'm going to find 1 squared plus my unknown side squared equals x squared. My unknown side squared is x squared minus 1. So my unknown side is the square root of x squared minus 1. And yeah, you can say there's a plus or minus there, which we might deal with later. But I'm just going to say it's plus for now. So it's going to be 1 over secant of y, which is x, times the square root of x squared minus 1. And then depending on how, so typically the way this is done is just to look at the graphs and say, okay, well, if we've done the graph where the derivative is always positive, then we need the absolute value of x such that the derivative is always positive. So if our graph for secant, sorry, for inverse secant was this one, a terrible one, in my opinion. Sorry, I know it's biased, but I'm biased against it. No, sorry, not the terrible one. Can I graph it? Maybe. Like this. If that's our graph, then we say, oh, the derivative is always positive. So we need an absolute value. So this is our graph. Then we say that y prime is equal to 1 over the absolute value of x times the square root of x squared minus 1. On the other hand, if our graph was the one that I consider to be the terrible graph personally, if our graph was this one instead, sorry, I know I'm doing these kind of slipshod here. The graph was this one that looked like this. Then the derivative is negative over here and positive over here. So I want my derivative to be just 1 over x times the square root of x squared minus 1. Now I feel like is where you're going to have some questions. So what's your question?
I feel like adding the absolute value is really arbitrary.
But it's not arbitrary.
I mean, I get that if we want the answer to be positive,
Well, we don't think it should be right.
if the answer to be right, but shouldn't the algebra itself give us the right answer? Like,
So-
we're adding something at some point to give us the right answer.
Sure.
But ignore the answer.
So let's think about this then this way. So if this is what we're doing, right? So if we're saying it's supposed to be this, then our outputs, our angles should be between 0 and pi, right? Just looking at the graph we've drawn, right? If I define, my inverse secant function, which is what I'm looking at, to be this particular function, then I'm saying my range is between pi and 0. Okay. So now is where I have to think about this a little bit, because really we don't get into this detail usually. I don't want to waste anyone's time, but I also want to address the question. So here's what I would say. If we're over in this section here, everything's fine. Right, so I'm over here in the first, when x is positive. Well, if x is positive, then the inverse secant is going to give me a positive output, meaning I'm going to be between 0 and pi over 2. And so if I'm between 0 and pi over 2, then I'm going to have positive, totally fine. On the other hand, if I'm over on this side here, well, then my angle was between pi over 2 and pi, which means secant is negative. And so is tangent. So really what I should have is well, if x is negative, I should have, see, this is where it's like throw some absolute values because it's what's right, even though it's confusing here. Secant of y should give me a negative number. So if x is negative, that's going to stay the same, but there's a negative there as well. So it should be.
That's square, no? Doesn't tangent positive?
What's that?
The number inside the square root, that's already a square. So it turns into positive.
Right, but you're forgetting about this. So the thing is, what I really want to say is we should talk about this individually some other time, because it's a small detail that, while interesting and maybe important, sure, we gloss over because it's minutia that, while again, maybe we care about, it's something we can avoid. So here's the answer to the other question was that I forgot you. I know I said your name once and now I've forgotten it. Sorry. To your question was that it depends on what your teacher has said. So for example, if someone asked us, what's the derivative of the inverse secant of x cubed? Your answer is going to depend on how your teacher has said that we have defined the inverse secant function and how they've talked about the derivative. So if your derivative has the absolute value, then your derivative has the absolute value. So one correct answer might be 1 over the absolute value of your stuff times the square root of your stuff squared minus 1 times the derivative of your stuff. But your answer could be without the absolute value. It could be the derivative of the inverse secant of x cubed is 1 over your stuff times the square root of your stuff squared minus 1 times the derivative of your stuff. And they are slightly different. This one, if you simplify this does simplify as 3 over the absolute value of x times the square root of x to the 6 minus 1, whereas this one simplifies as 3 over x times the square root of x to the 6 minus 1. They're different. So it does depend. And then sadly, that is the best answer I can give you. So what you all need to do if you're concerned about this particular thing is you need to ask your teacher, hey, how have you defined the inverse secant or inverse cosecant? Does our derivative have an absolute value or not? And if they are waffling on it, I guess I would refer back to the textbook. Whatever the textbook has done, that's what you should do. And I believe the textbook, actually, I don't know. I feel like the textbook does it with the absolute value, although I'm not, yeah, okay, good. That's what I thought. So if unsure, if your teacher is lame, doesn't want to decide for you, then you should go with the derivative of the inverse secant of x does have an absolute value. And similarly, the derivative of the inverse cosecant of x does have an absolute value. That's my default place as well. Has anyone talked about hyperbolic trig functions? Yeah? Okay. Bummer. No, they're actually not that bad at all. Since I feel like we don't have enough time to really get into the other stuff I want to talk about today, we'll talk about that on Thursday. Let's talk about the hyperbolic trig functions for just a minute, just because some of you might see it. I never learned it when I took Calc 1. It's not like a huge deal, but here's the thing. Someone might talk about it at some point. It might come up in 21B. It probably will come in 21B. And the other thing is it's easy. So hyperbolic trig functions in 15 minutes or less. Yeah, we have totally enough time. Really, they're not that bad. So first things first, hyperbolic trig functions are not trig functions. They are not trig functions. Good to know. They're actually exponential functions. So we define hyperbolic sine and hyperbolic cosine in the following way. Some people, so I will say you should never, in my opinion, you should never say sin or cos or tan. It just sounds terrible. Sine, cosine, tangent. But I will relax my personal beliefs when it comes to hyperbolic sine and hyperbolic. Because saying hyperbolic sine or hyperbolic cosine is a mouthful. People do say sinh and cosh for hyperbolic sine, hyperbolic cosine. I know they're throwing in like a ch there for sine h, but they do say hyperbolic sine, or the people do say sinh of x is defined to be e to the x minus e to the negative x over 2. And hyperbolic cosine or cosh, but I will still say hyperbolic cosine, is defined to be e to the x plus e to the negative x over 2. The reason they're called hyperbolic trig functions, or one of the many reasons, is they are similar to the trig functions in many ways. Their derivatives end up working out in very, very similar ways to regular trig functions. And some of the things about them that are true for trig functions are also true for hyperbolic trig functions. Meaning, just like the sine function is an odd function, so is the hyperbolic sine function. Just like sine of 0 is equal to 0, hyperbolic sine of 0 is also equal to 0. In fact, let me show you. Hyperbolic sine of 0 is equal to e to the 0 minus e to the negative 0 all over 2, which is, let's see, 1 minus 1. Oh yeah, that's 0. And hyperbolic cosine of 0, just like cosine of 0, regular cosine of 0 is equal to 1, hyperbolic cosine of 0 is also equal to 1. It's e to the 0 plus e to the negative 0 over 2, which is 1 plus 1 over 2, which is 1.
What are their functions? Like, why do they?
Why? Well, I mean, they exist because they're so that's a good question, actually. I don't have a good answer for like why we decided to call this particular thing, other than it shows up in places like this function is also shows up as a catenary, which is like kind of the thing you get if you attach a wire to two poles and like it hangs down below. That's kind of what the hyperbolic cosine function looks like. Yeah, it is definitely more related to physics. But one of the reasons we have decided to call them these things mathematical, and you might just see this show up sometime, be like, and no one like say it's that. But let's talk about what happens. Well, actually, let me talk about how they're even and odd first, and then we'll talk about how the other things look. So it's definitely an odd function, f of x equal to the hyperbolic sine of. Try not to make your h's and n's look the same. This function is odd. Check it out. F of negative x, which is hyperbolic sine of negative x, is e to the negative x minus e to the negative x over 2, which is really e to the negative x minus e to the x over 2, which is negative e to the x minus e to the negative x over 2, which is the negative of hyperbolic sine of x, which is what makes it odd. And similarly, the hyperbolic cosine is even. Hyperbolic cosine of negative x is equal to e to the negative x plus e to the negative x all over 2, which is just e to the negative x plus e to the x over 2, which is the same as the function you started with. So definitely odd and even, just like regular sine is not function, regular cosine is the function. And yeah, we got time. Because they are worth graphing. Here are what the graphs of them look like. So here's how people usually graph this, or think about graphing it. This graph has asymptotes. Very, very weird asymptotes. Let me show you what I mean. So we're going to think of this as e to the x over 2 plus e to the negative x over 2. And I'm going to graph just e to the x over 2 first. So e to the x over 2, if I just think about graphing that for a second, e to the x over 2 has a y-intercept at 1/2. So plug in 0 for x, I get y equal to 1 over 2. So here's my graph of e to the x over 2. And in a similar way, if I just graph e to the negative x over 2, oops, I blew it. I mean, it's fine, I can fix it, but that's not what hyperbolic sine is equal to. That's hyperbolic cosine. Let's just color over it here. It's terrible, I know. Forgive me. So e to the negative x over 2 looks like the same graph except flipped over. So it's going to be, let's make sure I get this right. I'm always bad at graphing the other direction. I don't know why it troubles me so, but I just am. Oh, yeah. Self-fulfilling prophecy there. Yeah. It should be symmetrical. Now here's the thing. If I add these two functions together, when I'm way out here and I add this a little bit, it's just going to be a little bit higher than that. So, whereas if I add them here, 1/2 plus 1/2 is 1. So basically, this hyperbolic cosine function is asymptotic to these. And again, it should be symmetrical with the even function. I know it looks terrible. I can see your face. But that's the idea. The hyperbolic cosine function is asymptotic to e to the x over 2 and e to the negative x over 2. Which is kind of weird to have those functions as asymptotic, but we do. And in a similar way, what I meant to start with, but didn't, if you graph the hyperbolic sine of x, which is e to the x minus e to the minus x over 2, or e to the x over 2 minus e to the negative x over 2. I'm going to graph that in a similar sort of way. I'm going to graph also an e to the x over 2 as an asymptote. I really just want the right side of it though. And a negative e to the negative x over 2, which is reflected in both the x and the y-axis. So it looks more like this. I guess I do want both parts of it. And then when I add these two pieces together, well, if I add this slightly negative, whoops, you can't really see that very well. If I add this slightly negative value to this very positive value, it's going to be just a little bit under it. And similarly over here, if I add this very slightly positive value to this very negative value, it's going to be slightly above it. So the inverse, sorry, the hyperbolic sine function looks like this. Found that much better. Kind of cool. Now, again, do you really need to know this? Probably not. It probably won't come up. Your teacher will probably never ever talk about it. But their derivatives kind of do come up sometimes in 21B. And the nice thing about the derivatives is they're almost exactly what you think they should be. So before we talk about the derivatives, let's define the rest of the hyperbolic trig functions. And we know what? You already probably know them. They're exactly what you hope they would be. Hyperbolic tangent is hyperbolic sine divided by hyperbolic cosine, which is all you really want to remember, actually. You could certainly write it as e to the x minus e to the negative x over 2 over e to the x plus e to the negative x over 2, and then cancel the 2's. But really, you should just remember, if you have to remember them at all, which is a long shot at the beginning, all you really want to remember is the definitions of hyperbolic sine and hyperbolic cosine. And then every other hyperbolic trig function is exactly what you think it should be. Meaning hyperbolic tangent is that. Hyperbolic cosecant, or let's do secant first, is exactly 1 over hyperbolic cosine, which is exactly the reciprocal of hyperbolic cosine. Hyperbolic cosecant is exactly 1 over hyperbolic sine, which is exactly 2 over e to the x minus e to the minus x. And hyperbolic cotangent is exactly hyperbolic cosine divided by hyperbolic sine, which is exactly e to the x plus e to the minus x divided by e to the x minus e to the minus x. But really, all you want to remember is these parts and these parts. Okay, now here's what's cool. All the derivatives work out almost exactly how you hope they would. Meaning, when I say almost exactly how you hope they would, meaning if you know what the trig derivative is, you know what the hyperbolic trig derivative is, almost. So let's see what we mean. If I want to find the derivative of the hyperbolic sine, well, let's see, that's the derivative of e to the x minus e to the minus x over 2. Or it might be easier to think of this as the derivative of 1/2 times e to the x minus e to the minus x. So 1/2 hangs out. Derivative of e to the x is e to the x. Derivative of e minus e to the minus x is minus e to the minus x times minus 1, or plus e to the minus x. Hey, what's that look like? I'm sorry. Hey, what's that look like? It looks like hyperbolic cosine, which you would have hoped for, right? We know the derivative of regular sine is regular cosine. We were hoping that the derivative of hyperbolic sine was hyperbolic cosine. I don't know. It might. I don't think it comes up a lot. A better person to ask that question to would be Duff or Casey, because they actually know about physics. Speaking of, if you have to take physics at some point, we also offer physics workshops and co-classes. So Duff and Casey are the guys for physics. They definitely are super helpful. They know all about it.
Physics co-class.
So either Duff, Harold, I think it's last name. Do I know Duff's last name? I should. Or Casey. And but there, so if you go to the tutoring.ucdavis.edu/physics website, you will find the information there.
Could you define normal trig functions in the same way, so without using trig functions in terms of exponentials?
No, definitely not.
So it's only the hyperbola.
Right, yeah. These are very much not trigonometric functions. We have happened to give them these names because they have a lot of properties that are in sync with how the properties of regular actual trigonometric functions work. But no, we definitely cannot do that. Oh, so then the derivative of hyperbolic sine is hyperbolic cosine. What do we hope for the derivative of hyperbolic cosine to be? What would you all like it to be? Right, that's what we'd like it to be. We're so close. We're not quite there. So here's what we get. Derivative of hyperbolic cosine is the derivative of 1/2 times e to the x plus e to the minus x, which is going to be 1/2 times the derivative of e to the x is e to the x. Derivative of the negative x is negative e to the negative x. So we actually don't get negative hyperbolic sine, we actually get positive hyperbolic sine. Which is kind of cool. So here's the way the rest of them work. They all are what you think they should be, except all the ones on the left are positive, all the ones on the right are negative. So what I mean by this is the following. The derivative of hyperbolic sine is hyperbolic cosine. The derivative of hyperbolic cosine is indeed positive hyperbolic sine. And we'll show this later if you want. Derivative of hyperbolic tangent is indeed positive hyperbolic secant squared. And then all the ones on the right hand side are exactly what you think they should be, except they're all negative. So the derivative of hyperbolic cosecant is in fact negative hyperbolic cosecant hyperbolic cotangent. The derivative of hyperbolic secant is not positive, it is negative hyperbolic secant hyperbolic tangent. And the derivative of the hyperbolic cotangent is the negative hyperbolic cosecant squared. Almost exactly the same as the trig derivatives, but not quite. All these ones are positive, all these ones are negative. I would love to show you how this actually works because there is a hyperbolic trig identity, which is kind of cool. But we're out of time. But it could anyway. You're welcome to go. I'm going to show you anyway. So, fun fact. So in regular trig functions, I tan and get sexy. In hyperbolic trig functions, I don't tan and get sexy. It's true. 1 minus hyperbolic tangent squared secant squared is equal to hyperbolic secant squared. And so then you can use this to take the derivative of hyperbolic tangent is the derivative of hyperbolic sine over hyperbolic cosine, which is bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. Oh, thank you. And then that ends up being exactly cosine squared over cosine squared minus sine squared over cosine squared, which is exactly hyperbolic secant squared. The other hyperbolic trig identity that I didn't write down, but is actually what we usually use for this, is that the hyperbolic cosine squared minus the hyperbolic sine squared equals 1. All right. I've said too much. Not really. I've said enough. Next class, we'll talk about relative extremo, first derivative test, second derivative test, concavity, all that kind of good stuff.
We already talked about with the rates here.
We have, yes. That doesn't mean we couldn't review it again.
Is it on Zoom?
You definitely, well, it's on Canvas. You can also, if you don't go through Canvas, you can also just find it on YouTube. Like all the videos on Zoom are on YouTube. I'm sorry, on Canvas are on YouTube. YouTube also has the videos from previous quarters as well. But yeah, they're totally on Canvas. And they're also labeled pretty well on Canvas, so you should be able to find it without too much searching around. You're welcome. All right. Enjoy the rest of your day. You're welcome. Yeah. It's good to review this stuff though.
Yeah, it's very nice that you're doing this in class right now. So it's very good.
Good.
Two quick things.
Sure.
One is, I was gonna show you something, I just found out about it. Is it okay if I go from the?
Yeah, go ahead.
So, this was, I thought this was a great